Okay, welcome to Chapter 8.1. You're in Chapter 8 now, Integration by Parts. This chapter is integration techniques, and the first of these techniques is integration by parts. Before we get into integration by parts, we're going to do a little bit of a review of back to Calculus 1, the derivatives, in particular product rule derivatives. Do you remember how to do the derivative of a function like this, where you have sine of x times cosine of x? You apply the product rule. The derivative of functions g times function h, the product of these two functions, is equal to g prime of h plus g times h prime. So the derivative of sine times cosine is equal to cosine times cosine plus sine times a negative sine, which becomes a negative sine squared. That's how you would do a derivative of the products of two functions. And the reason we bring this up is because we are actually going to take this backwards and do an integral based on the product rule. We can't do it for all products because some of them are just not obvious as to what they would have started from as a derivative. But there is a fairly large family of integrals that can be simplified using a product rule. So let's take a look at exactly what this integration by parts is. Here's the product rule in red at the top of the screen here. You take the integral of both sides and you end up with f times g is equal to two integrals, the integral of f prime times g and the integral of f times g prime. And so this is the basic framework of our product rule integral. But let's take this a little bit further. If we make a few choice substitutions, because with these u's and v's are a little bit easier to read than the fx, g of x, f prime of x, gx, and so on like that. I made some substitutions. I even color-coded them to make it a little bit more visually clear of what's going on. So the f of x becomes a u, the g of x becomes a v, and I've got their derivatives too. And we reorder these a little bit by just adding and subtracting across the equal sign, and we end up with the integral of u dv equals uv minus v du. And so far you might not have seen the significance of this, but what it means is that if you have an integral that is particularly difficult, you could potentially simplify it into two terms, of which one of those is an integral, the other one isn't, which the uv would require no additional work. It just gets copied down. The integral of v du may be a simpler integral than what you started with. And so that is the purpose of integration by parts. It takes complicated integrals and turns them into something easier. So here is the formula as written in the book. The pretty much same thing I had just above on the previous slide. So let's take a look at an example. In red I have the identity copied down here, and it's on most of the slides, so you can see that as a reference. You have the integral of x times sine of x over 2. And so the x is colored in blue, the sine is colored in green. And you make a choice of, okay, which one am I going to call u and which one am I going to call dv? And I decided that u should be x and that dv should be sine of x squared. At first, it's going to look like an arbitrary guess as to which one we choose to be u and dv, but there's actually a little bit of an educated guess with it. The catch is that if you guess them wrong, well, it just won't simplify. You won't get any advantage out of it. But if you do choose correctly, you will end up with a fairly simple integral at the end. So these are the ones chosen correctly. You have two possible ways that this can turn up. So, and all these have been set up to go in the proper way. I'll do one in class where we guess wrongly. So let's see what happens with these choices of u and dv. We go on and I went on and took the integral of dv to find what v is equal to. So this v that you see right here was derived from this dv term. I took the derivative of u to find du. So this one and this one were derived from the u and dv. So let's go on and fill those in. I've color-coded these so it's easier to see, because on some of these it gets sort of tricky to keep track of. So we have x times sine of x over 2. That's what we started with. You substitute these values in. You've got this negative 2x times cosine of x over 2. There's no integral there. That part of the answer is done. That is part of the answer right here already. What you're left with is the integral of negative 2 times cosine of x over 2. That's pretty good because you know what the integral of cosine is. And so let's take this negative 2 outside this integral. It's a constant term. We don't need it in there. 2 negatives is a positive. So now you've got this positive 2. And on the inside, it's just a cosine of x over 2. You perform this integral. You can do an integration by substitution by, let's say, substituting w equals x over 2, and then you have cosine of w dw. What this 2 is going to happen is it's going to end up being a sine and then multiplied 2 times sine of x over 2. The 2 times the 2 will multiply to be a 4. So yes, this 2 in the denominator comes up in front when that becomes a sine. And this, well, this negative 2x cosine, that's part of the answer. It just copies down. That's it. That's your result. Pretty cool. That's integration by parts. Had you substituted incorrectly, you would have had an x times the sine of x over here, or something like that. You would have had a product of an x and a cosine term, and you'd be like, well, what was the point of that? I ended up with something just as bad as what I started with. That's the worst case scenario, and you'd be like, oh, okay, well, we got to do this a different way. So here's another example. Anytime you see a function that can be integrated or differentiated an infinite number of times, like e to the x, or sine of x, or cosine of x, where sine or cosine of x repeat every 4 differentiations to give the same value it was before. E to the x integrates or differentiates every time. So that one more or less stays the same. But you have this x squared here. You differentiate this once, you got 2x. You differentiate it twice, you got 2. You differentiate it a third time, if you wish, you got nothing. So this is a case where integration by parts can certainly work, because you have this term that can be differentiated an arbitrary number of times, and you've got this term that can be infinite. So you got to for sure make sure you get these choices correct. And we have the u is in the integral right here on this in red. And the idea is that the u term is going to turn into a du over here. And well, the e to the x, if we choose e to the x to be u, we're going to have an e to the x here, we're going to have an e to the x here. And that simplified nothing. So if we choose u to be x squared, then over here on this side, it's going to be 2x. And that is simpler than having an x squared. So that is sort of the educated guess that goes behind the idea of choosing your u and your dv correctly. So the u is going to be x squared, and the dv is going to be e to the x. From this dv, I do the integral and I find e to the x. That wasn't bad. From this, I do the derivative and I find 2x dx. And now substitute them back in. We've got this x squared e to the x equals x squared e to the x minus 2x dx times e to the x. And now notice that with this, just by making these substitutions, notice we didn't really do much. All the integration differentiation was done in this step where we had these four terms. But down here all we did is just substitute these values in, and we got something closer to the answer here. This right here we're going to save for later. That's part of our answer. What we have to work with here is this 2x times e to the x. So this is going to be a problem within the problem we have to solve. We need to repeat this process one more time for this value, and then whatever answer this is going to substitute back in here inside parentheses. Everything, this subtraction will subtract everything in here that's this answer, this integral. The goal is that that x squared turned into this 2x in green. It reduced by 1 degree. It's 1 degree less of a polynomial. That simplifies this integral. So here's our problem within a problem, 2x e to the x. So we're pretty sure, like, hey, we want this to be the u because we want our du to be simple, which in this case is just going to be 2. So here's our u is 2x. Our dx here is going to be e to the x. It's going to be the same as what the integral of that's going to be the same. It's going to be e to the x. In the second term here we have 2x, which is u, times e to the x. And our last part here is going to be our v. Our v is e to the x, the integral we found, times our du, which is 2. So this is just 2 times e to the x after we make our substitutions. This integral is pretty easy, especially once you take this 2 outside as a constant term. Integral of e to the x is e to the x. That's our answer. That's what I got here. Negative 2 e to the x plus c. And so this was what our original problem was. And we need to substitute this answer in for where this green is. So that's our key. So you substitute that in, and you will have the final answer. So I put the parentheses here to encapsulate this in. Take this negative of all of them, and I end up with these two extra terms, 2x e to the x plus 2 e to the x. And this is our complete answer. It has three terms plus a constant. And that's a pretty cool case for solving integration by parts. There is a shortcut to this. This is one of those dirty secrets. They call it tabular integration. And if you have a function g of x that can be integrated easily, like e to the x or sine of x, or I shouldn't really say one more easily than the other, because that's actually misleading. I think I actually said the wrong thing. See, f of x is one that gets differentiated a few times before it becomes 0, and g to the x is the one that you'd retain as the dv. So anytime you have a situation like this, it wasn't fair for me to write easily here, because that's an opinion, and opinions are often wrong. Ask anybody on Facebook. There's a lot of them there. So there's actually a shortcut for this type of layout, and you're going to love this. And so, for example, we have this integral of t squared times cosine of t. On the left-hand side, we have f of t. That's equal to t squared. F prime of t is 2t. F prime prime of t is equal to 2. So we have the t squared. The derivative of t squared is 2t. The second derivative of t squared is 2. We have our signs. These signs must alternate. They start with plus, then they go to minus, and then they go to plus. And then we have our integrals. First integral, cosine. Integral of cosine is sine. Second integral of cosine is negative cosine. Third integral is negative sine. And now here's a dirty trick. You take your t squared times this result, and you get t squared sine of t. Oh yeah, there it is. You take this 2t, you take this cosine of t, and that's a negative 2t cosine of t. Notice we have this negative that's reflected right there. And now last part here is 2 times negative sine of t. That's that negative sign is right there. So that's our third term there, and that's added in. But unfortunately, you're adding a negative number, so it's subtracted. And these two negatives become a positive as well. So we have a couple places where sign is changed. And so here's an example, another example of tabular integration. So we have x cubed times e to the x. So the first term positive, second term negative, third term positive, fourth term negative. They have to alternate signs. That's part of the format of tabular integration. The x cubed here is the first term. Its derivative is 3x squared. The negative comes because it's the second term. The derivative of x squared, of 3x squared, is 6x. the derivative of 6x is 6. These negatives are come from the sign changes of going positive to negative. And e to the x, well, it stays the same all the way through. That's an integral. For the second term, you have to take an integral. Integral of e to the x is e to the x. Second integral of this e to the x is e to the x. Third integral, the fourth integral, it doesn't matter. It's still e to the x. And you take these and you just add them up. How easy is that? Oh, I shouldn't say easy. That's an opinion. Because it's actually very wrong to say anything in math is easy. That never works out. Because if I say something is easy, then you might feel really stupid because you don't get it. And if it truly was easy, you would have learned this already in elementary school or something. But it doesn't work like that. This is actually really hard. So, which is why it's in college and not in high school or anything earlier. But then, if it's easy and you realize that for you it is easy, then you become complacent and you think, oh yeah, no big deal. I don't really have to worry about this. And then before you know it, you realize that you don't know it. And so it never works out to say anything is easy. Nothing good ever comes of that. So I'll tell you that this is hard, because the truth is that for practically everybody it is. So yeah, evaluating definite integrals, almost the same as regular integrals. The key part to remember is that this section in the center here must be evaluated from a to b as well. Anytime you have these middle terms, they must be evaluated. That's the main difference, the main thing to be concerned about. You don't forget about those guys. So here's an example from 1 to 2. You have this graph of x times the natural log of the natural log of x. And so this is a graph that is increasing in the diagonal direction and is actually slowly increasing, even a little bit more because it's multiplied by log after all. And so there's definitely going to be an area under this curve. It's also defined within 1 and 2, so this is perfectly valid. And so we're going to make some assignments of our u and our dv. If we make this part u, then this part, then our du is going to be pretty simple. This u is going to be an x. The derivative of x is 1. So our du is equal to 1 dx. So that's a pretty good substitution. And so with there's so if you do that and you go through it, you might run into you also might run into problems, because I did it a different way down here, and what you end up with doing is that this will probably not simplify correctly if you make that assumption. So keep in mind that you might screw up to some degree when you do these. And so in this case, the u is equal to a natural log, because the du is also pretty simple here. The derivative of natural log is 1 over x. And that would end up canceling out an x out of the v. And so that's That's all. That's a substitution you can try as well. The first substitution I suggested might actually work too. I think it would. And so this might be a good one to do in class as well. Maybe do it both ways. And so but the method that's known good is with substitution of u equals natural log of e. And so putting that in, we have our u and our dv is equal to x. And so because our dv is x, our v must be the integral of that, x squared over 2. And the derivative of natural log is dx over x. We substitute those in. Here's our u times v. Our u is natural log of e. That's right here. Our v is x squared over 2. And now what happens is that because we chose u to be natural log, that we end up with 1 over x. And as these cancel out, and ends up with x over 2. So we can even take out the x. I mean, we can even take out the 2, and we're just left with an x. The integral of x is x squared over 2. I'm scribbling in here stuff that I've already done the work for. And so here's our formulas as they have been simplified. And we just basically substitute in our values. And so something's not right here. Yeah, that's that log base e of x disappeared. Wow, and, the creepy thing is that I didn't fix that from the last time I taught this course. And so you substitute these values in, and you acquire this value. You perform these definite integrals, or this definite integral as well, and you'll get x squared over 2, which that 2 comes out and becomes a 1 over 4. Oh, that was weird. I just heard a Windows sound, but and I don't have Windows booted up, or at least I didn't. So anyway, it simplifies down to this answer. And yeah, this would be a good one to do in class as well. We'll do it both ways and see what happens. So I'll leave this as an element of suspense for you. So have fun. I'll see you.